Uh, this was this is the challenge 2 years ago. So sorry, 2023. So last year's challenge was all about projectile motion. This year's challenge is currently a hot secret. Will be revealed in March, and the previous year it was all about gravity and astrophysics. So particularly solar system orbits. So what we're going to do is going to have a little look at some of the physics of that in a moment, and importantly how we can then turn that into some code. And so sort of by popular request, what I'm going to do is, and I think we'll do this for most sessions, we'll do a bit of live programming as this session progresses. And I'll keep this quite simple, but it has a sort of flavor of what we're doing. Some of the code I'll show you are quite large projects. Some of the things are very, very simple. And quite a few of the slides we'll mention today are actually from the computational challenge that involves solar system orbits. So you'll see the sort of format if you're new to this. Okay, so let's just kind of get into the screen. Can I just confirm, can you see the splash screen okay? Is my voice coming across nice and clearly?
Yeah, all good.
Fantastic. All right, okay, so a few busy things, but we'll go through this nice and slowly. This is the kind of guts of what's going on. So here we go. We've got the man with the enormous ruff, almost a sort of solar system orbit in itself. That is Johannes Kepler. And the slightly larger image is, of course, Isaac Newton. So, of course, Kepler preceded Isaac Newton. And an amazing feat of deduction and reasoning predicted these three laws. First one is that the orbits of the planets about the sun, which, of course, is general for any kind of two-body system interacting via gravity. These are ellipses. Most of the system we'll look at today will involve circular motion, to keep it simple, but in general, it's worth noting these are ellipses. So we can see an ellipse in the figure at the bottom. So we have a semi-minor axis, 2b, which is the sort of like the y extent, the width, usually the lesser part, and the semi-major axis, the wider part of my ellipse. And of course, a special case of an ellipse is a circle when b equals a. So that's Kepler's first law, orbits are ellipses. Kepler's second law is really interesting. And if you look at the sort of green areas we've got, so this represents a constant interval of time. So the planets, the little blue object, that sweeps this sort of green part from the sun. I'm assuming in this case that the mass m is much, much bigger than mass little m. All right, so the center of mass of their collective motions is in the center of this kind of red star here. If you've got something like, I don't know, Pluto and its moon Charon, they will move about their common center of mass called the barycenter. All right, but to keep it simple, we're going to look at sort of a very large star and some planets going around it. And if you look at the sort of motion of the planet when it's a bit closer to the sun, the green areas are identical. So in equal times, equal areas are swept out by the orbit. That's Kepler's second law. And its third law, which we're going to be using most, is the one at the bottom. So the period squared, I'm going to use P for periods. The time it takes the planet to go round the star goes as the cube as the semi-major axis. All right. Now, we're going to simplify that and call that the radius for circular orbits. So why is that a good idea for our solar system? Well, if you look at the picture at the top, that's a moderately accurate drawing of our solar system. And you'll notice that the orbits by eye are very, very circular. If you go and zoom in and look at Mars, which is the red one, you'll see that's visually a bit more elliptical than the others. But to a good extent, a sort of first approximation, most of the orbits are circular. Gotcha, you might think, is Pluto. Okay, that's not really a planet, but hey-ho. That's actually a different plane. So it's tilted from the plane of the ecliptic, which is the plane that all the other planets orbit in. And so you see a sort of like a sort of distortion in 2 dimensions. So what's going on? What did Newton add to this? Well, he added a kind of reason why this all works. So we have the force of gravity, which is based on the product of the masses of 2 things divided by the square of the distance between them. So r in this case is the distance between the planet and the star. And there we go, m and little m are the masses of those things. And big G is what turns masses and distance into force in newtons, which has a very small number. Right, despite the fact that it's a very important universal constant, it is tiny. And for those of you who studied electromagnetism, amazingly, the ratio between the gravitational force and the electrical force between, say, 2 electrons, the same distance, is about 4.2 to 10 to the 42. So that's the electrical force divided by the gravitational force. So you need an entire planet to have serious gravity. What else have we got on this page? Well, we've got an expression for the polar equation of an ellipse. So if I want to actually plot this blue sort of ellipse in terms of angle, let's say I define an array of angles going 0 to 2 pi radians, I can use this equation to work out the radius and then some trigonometry to work out x and y. So that would be a nice thing to, maybe a first thing you might want to try when plotting some orbits, to see if you can plot an ellipse. Epsilon is what we call the eccentricity of the ellipse, and it's related to the semi-major axis and the semi-minor axis. Obviously, for a circle, b equals a, and the eccentricity is 0, and then r equals a. So no surprise there, it's a circle. So there we go. We're going to be using Kepler's third law quite a lot today. What else have we got? So there we go. It's another sort of like enlargement of the picture and some words with Kepler's 3 laws. So orbits or ellipses, the areas are equal areas swept out in equal times. In fact, there's an equation for it, because from Newton's laws, you can derive all this stuff. I won't do that today, but if you look in my my notes, you can pick through on the Eclecticon, plus any other book you could choose about this. You can work it all through. And I think everyone who wants to study physics, perhaps up to university level, should go through that analysis, starting with circular motion of orbits, then building towards the 2-body problem. And perhaps not the 3-body problem, that's a bit harder, but that is a good thing for you to do. Anyway, so that's visually what Kepler's third law, the 3 laws are. Okay, so perhaps just a little diversion, and this is how I introduce gravity to my sixth form. So if any of my sixth formers are on the call, or people I've taught previously, hello, big wave from me. You might remember this from your first lesson on gravity in your upper sixth with me. So it's a little bit busy, this diagram, so I'm just going to sort of like hopefully sort of annotate sort of a certain few parts of it. So this is possibly how Isaac Newton came up with the inverse square law. So the thing we met before, this idea of the force of gravity going as 1 over r squared. And the idea is you sort of consider how far the moon might fall in 1 second. Now, this diagram is most definitely not to scale, but like a lot of things we can draw in geometry, we can get the essential features even if the scale is completely bonkers. So in reality, the moon is about 60 Earth radii away, and that's been known since antiquity. So let's just say what happens. The moon goes around the Earth. Let's just say we figured that out. So in 1 second, let's just say we can draw a triangle here, and it drops by delta. That's the distance. That's the map. The moon falls. Of course, it's moving around in a circle, but in a sense, it falls by distance delta. All right. So let's kind of work out what that might be, and we can do it in several ways. So just from geometry, we can do some Pythagoras. So if you kind of look in the top left-hand corner, 60 Earth radii is the sort of vertical side of my right-angled triangle. We've got D here, so we're squaring both of those. My hypotenuse is my fall distance plus 60 Earth radii, the Earth-Moon separation, all squared. If we expand those all out, so I hope you can follow the sort of second step and maybe the third step. And basically, we can kind of get rid of the delta squared compared to the other parts. So we're going to assume that's very small compared to, for example, the radius of the Earth. And what you end up with is this fall distance goes as the square of the distance that the moon moves horizontally over 120 times the Earth radii. So let's work out how far the moon travels. And you might say, hang on a minute, that horizontal distance isn't the same as the arc length. Well, we're talking about 1 second out of, 28 days. So this is actually going to be a really small angle. So that length and that arc are basically the same. So 2 pi times 60r, right? And that's going to be the sort of, that's the circumference, right? And we divide that, we work that. So if in 1 second, how far is it going to travel? So that's the amount of time in a month. So in an orbit of the moon. So if we divide the circumference of the orbit by the number of seconds, we've got the distance that the moon travels in a second, which is just under a kilometre. So there's some nice numbers here. So in 1 second, the moon travels about a kilometre. And so therefore, we can plug into our little equation here how far it will fall. And it turns out it's about a millimetre. So there we go, some pub quiz facts. The moon travels about a kilometre every second. and falls about 1 millimeter. Now, here's rather a nice thing. So if we say that the fall distance is half AT squared, Galileo style, right, constant acceleration motion, all right, we can basically work out if we can get some model of the strength of gravity at the moon, all right, we can get the same thing. So how do I get 1.3 millimeters? Well, G moon divided by the strength of gravity on Earth, we get our 1.3 millimeters if the ratio of my G's is 1/60 squared. So if you think about it, that means that the strength of gravity has got to go as an inverse square law. So if the moon's 60 times as far away, the strength of gravity is 1/60 squared, that of the surface of the Earth. If you do that and plug in for G moon, you'll get the same fall distance as you've worked out just from orbits. So obviously that's not a proof, but it actually gives you an idea of where the inverse square law comes from. So in summary, we do a nice little circular diagram like this. We do our geometry. We work out the fall distance is 1 millimeter. The movement of the moon is about a kilometer. And in order for the fall distance based on half AT squared to be the same, we need our gravity on at the moon due to the Earth to be 1/60 squared that of the at the surface of the Earth. So in other words, 1/r squared. There we go. So that's moonfall. So what could you do computationally? Well, I guess you could kind of represent and draw this, but there we go. So that's an introduction to universal gravitation. Any questions before we actually get on with some modelling? Any in the chat?
No, just worth pointing something out because we're getting it very often. In terms of physics for the computational challenge, a lot of it will be given inside the challenge. So you don't need to know all of this. You don't need to have done absolutely everything in school. You don't need to remember everything right now. So don't worry about all of that.
Absolutely. So the idea of this course, particularly if this is your first visit, we're going to give you a kind of broad brush overview of the physics of a particular topic. In this case, gravity, astrophysics. Some of it you might have studied, some of it you think, oh, that's quite interesting and new. And what I'm going to do is come up with a few projects that are associated with that to give you a flavour of how the challenge is going to be. And as Nina says, she's absolutely right. The challenge that will be released will have all these facts in there, all the physics. There'll be simulations that I've done, and quite a lot of the challenges will go, well, here is a diagram or a picture of a simulation. Try and represent this in a language of your choice. So it's a bit like I'm giving you the recipe book and you're the chef and you're going to make your souffle. Okay, other food item analogies are available. Right, so here's another little thing which might be quite fun, just to look at the idea of the gravitational field strength. So this is the same as the acceleration due to gravity. So big G times the mass over r squared. If you plot that, that's a nice thing to do. You get a 1/r squared here. All right. So what I'm actually plotting here is that divided by the sort of strength of gravity on the Earth. So at the surface, the ratio of G to GR is 1. All right. That's at the surface of my planet. And I'm also plotting my x-axis as a radius divided by the radius of my spherical mass. So this is now a completely general curve, regardless of the mass and the radius of your planet. Of course, you could scale those if you want to be realistic for any planet. So that would be 9.81 for the Earth, about 1.3, I think, for the Moon, something like that. So what's quite interesting is that when you go inside a planet, the strength of gravity only depends on the enclosed mass. The sort of shell around it all cancels out. So when you're inside a sphere like this, the mass is 4/3 pi r squared times the density. So if you plug that into this little equation, you'll notice that r cubed cancels with r squared, leaving a linear factor of r. So what happens is that the strength of gravity gets less and less and less, and so it's 0 at the centre. Now, here's a question. So this is probably more for those who've studied at sixth form, but who knows? If you've got a force which is proportional to the distance, so think on springs, right? What is the motion if I was to drop a mass, say, at the surface? What would it do if I drilled a hole through my planet? What would the motion kind of look like? Let's pop some answers in the chat.
Yeah, simple harmonic, accelerate, go back and forth.
Yes. So what we can do now, I think there is a very bad, well, possibly depends on your taste. There's a film with Colin Farrell in it that involves this principle. That's a plot device. So I think it's called The Core or something like this. I may have got that wrong. But basically, there is a hole drilled from London, I think, to Sydney. I think that might be just about right. And you basically get in an elevator and it sort of takes you to the other side of the world. Well, I have an example of this. So if I come out here, so here's MATLAB. And we're going to go for one I've called gravity clock. And so I'm going to run this and hopefully you can see this rather anarchic clock. But there we go. So I think this is, I'm not sure this is exactly the, oh yeah, no, that's right. That is for the Earth. So I think this is the average density of the Earth is 5,513 kilograms per cubic meter. It's mostly made of iron. And so what I've got is I've got this sort of thing going around the Earth in circular motion with a period of 84.4 minutes. And so you'll notice that it will intersect with my little star, which is undergoing simple harmonic motion through my diameter. So it reaches its fastest speed in the middle, and it gets to zero speed as it gets to the end. So as long as you step off, you're right. And rather nicely, it's about 42 minutes is one diameter. So yet another example of where 42 crops up. So there we go. That's a sort of cool little problem. Right, let's go and have a little look. So here we go. So this is something that's in my book. So I grew up in the 1980s, and of course, Transformers were the best toys ever. So the Transformers live on Cybertron. Of course, these days you might have seen them in the films. From my time, it were these little plastic figures that transformed. And there we go. So what's interesting, as long as your planet has a constant density, you undergo simple harmonic motion. The X double dot means acceleration. So this is the formula for simple harmonic motion. The acceleration is minus times the distance times this factor, 2 pi over the period squared. So when you're looking at oscillatory motion, the game you play is spotting the difference between your formula, this is the one for gravity, and this one here. And from that, you can derive the period. So in our case, the period is the square root of 3 pi over big G times the density. And that is true regardless of the size of your planet. So I think Cybertron in the Michael Bay films, I think it's Michael Bay, isn't it, is rather larger than Earth, but maybe the density is the same. I think I've used titanium. So there we go. So Cybertron, it will be a bit longer. Okay, there we go. So some pop culture here today. Right. Okay. So there we are. Right. So let's get back to our Kepler's laws, and let's start to build a little simulation. So these are some of the parameters of the solar system, and this is going to be a nice approximation that we can use for our solar system. So if we've got Kepler's third law, and there's a 4 pi in it, G, and the masses of the planets, and A is our radius. If we write that, if we basically ignore the mass of the planets, so we can put a little approximate sign, so get rid of the little m. And for Earth, 1 year squared is 4 pi gm sun times an astronomical unit. So an astronomical unit is a very long distance, about 1.5 times 10 to the 11 meters, the distance between the Earth and the sun on average. So rather than using meters, that's rather a ridiculous scale for things like the solar system. So we're going to use astronomical units and years as units that make sense. And when you're doing models, you want units that we have a human cognition of. So things about 1 to 100, something like that. So all we have to do for Kepler's third law is say the period goes as the semi-major axis, let's call it the radius, to the power of 1.5. So what we're going to do is we'll build a little model, and let's go and plot maybe the Earth's orbit versus Mars. Let's go and do that. So I'm going to load up MATLAB. So this is your opportunity, if you want to do some live coding, to give that a go. Right, so let's go. I'm going to come out of this, and here we go. So I'm going to go and make a little file. So in MATLAB, this is a development environment. So you can see some folders here, and I can type commands in this little box. By typing word edit, I'm going to create a text file, which I'm going to call, let's call it Astro. Right, I'm going to give it a commentary. So that's what it's called. So this is going to be a demo. Actually, I'll do it at the top so we can maximize our space. So demo of solar system orbits. Okay, I'm doing this live, so there will be spelling mistakes and possibly coding errors, but that's how it all goes, right? I've got to be brave about these things. Right, so firstly, I'm just going to go and save this. So save as, and let's call it Astro. There we go. All right, so I've got a little .m file. That's just a text file of what we've got here. So always start off with commentary and then figure out the lingo. So what we're going to do, let's go and define some orbits. So we'll go for the radii first in astronomical units. So we'll go from R1. Let's go for Earth. Well, R Earth is going to be 1, and we'll go for R Mars. That's going to be, so for Mars is 1.523. 1.523. So this is the orbital radius in astronomical units. Okay, so we can now work out the periods. So P Earth, well, that's obviously 1. And then P Mars, that's going to be R Mars to the power of 1.5. Okay, so that's going to be orbital periods in years using Kepler-3. All right, hopefully all good so far. So if you put that to a calculator, in fact, we can do that. I just save and run that. I press the run button, and hopefully that should actually run that. Oh, I'm in the wrong place. I think so. Yeah, here we are. You can see my numbers here. So P Mars is 1.88 roughly years. Okay, so that's the orbital time of Mars, and I think that's about right. Yeah, 1.88. Fantastic. Right, so what we're going to do now is we're going to define a timescale. So if we want to plot some orbits and importantly later maybe connect lines between them and do all sorts of stuff, or maybe have an orbit from the perspective of Mars rather than the Sun, that would be fun. We want the same timescale. So we're going to go Newtonian on this and define some time. So T is going to be a linearly spaced array. I'll show you what that means. Between 0 and, well, what's the largest period? It's Mars, isn't it? So let's go for 10 times P Mars. P Mars, okay. And let's have maybe, I don't know, 5,000 data points. Okay. So if you're not sure what that means, let's do linspace between 0 and 10, and we'll have, just for fun, 11 data points. And you can see now we've got all those values, actually 0 to 10. So in fact, yes, that gives us integers. If I maybe have that to be 20 data points, you'll see it's got some non-integers. If I go for the answer and I transpose it, you can see that as a sort of column vector here. So linspace is a really good generating function in MATLAB to create a linearly spaced array of numbers. I think like a sort of column in Excel. And then we can do mathematical functions on that and plot things. So if you're doing Python, you want to use something like NumPy or possibly a list. That will also work. Okay, so what we'll do, we'll create time array in years. Okay, right, and now what we want to do is work out the x and y coordinates of my orbit. So to do that, we're probably nice to work out what the angle of my planet is, theta, maybe versus time. So what we'll do is we'll have theta Earth, and what we'll do, just to keep it be fun, we'll start off with a sort of random angle to start off with. So 2 pi radians times rand, that's a random start angle. And then what we'll do, as that varies with time, we'll say, well, it's going to be 2 pi radians times the number of periods. So times t divided by p Earth. Now, I know p Earth is 1, but we might want to change this code so that could be any other planet. So we've got a random phase, so a random angle to start off with, and then we've got 2 pi radians times the number of periods. Okay, so those of you doing courses in waves, for example, that's how we set the phase of an oscillation. And let's just go and do it for Mars as well. So theta Mars, so this is the angle, and we'll have that P Mars down here. Okay, so that's the angle of my orbit. If I just sort of show you, if you've just joined, that might be a good way of looking at it. So if we look at our original diagram, here we go. All right, and remember, we're going for circles rather than ellipses. but we're going to go for an angle measured from the horizontal going anti-clockwise. But we're going to start from a random place, hence the 2 pi times rand. So if I do rand here, and I do rand again, you'll notice I get a different random number between 0 and 1. Okay, so maybe if I can put that here, I hope that's not too bad. So this is the polar angle. All right, so it's going to be an array or vector of planet orbit polar angles. Okay, polar angles, angles from the horizontal. Right, now let's turn to X and Y. So it's time for some trigonometry. So X Earth. Right, actually I might go for E for, let's keep the Earth, let's keep the subset. The idea when you're programming, you want it to be human readable, okay, but not perhaps too verbose. So X Earth is going to be, well, R Earth, all right, times the cosine of theta Earth. All right, so we're resolving, all right, our vectors here. So radius times the cosine of the angle, and then we've got Y Earth is going to be that, it's the same, but we're using sine, okay? And let's do the same thing for Mars. Oops, I need a Y Earth here. Let's do the same for Mars. So all we need to do is change Earth to Mars. So quite a lot of programming is copy and pasting accurately. And there we go. Let's change Earth to Mars. I could use copy and replace, but there we are. I think that's all right. Okay, so this is going to be the XY coordinates in astronomical units. Okay, so MATLAB, like a lot of languages, will plot in Cartesians rather than polar things. So now we've got the X and the Y. Let's go and plot it. So there we are. I will give a space here. And MATLAB's lovely. If you just issue a plot command, it will just do it. So X Earth, Y Earth. And let's have a blue line for Earth. All right. So in MATLAB, you kind of define your variables, and there are sort of pairs of parameters where you can set things like, you know, the line thickness, the color of the line, everything you like. All right. What we'll also do is we'll go for the same thing for Mars. Okay, so we'll go for X Mars. Oh, do apologise. I'm going to turn my phone off. There we go. Sorry about that, everybody. And we'll go for Mars. And there we go, Mars here. Brilliant. Okay, and Mars, let's go for a red line. So what we'll do is we will plot the orbits. Plot the orbits. Now, you can't get much simpler than that. Issuing a plot command, and that will do everything for you. Not every language will have you that inbuilt functionality. Let's just have some parameters here. So X label is X in astronomical units, and the Y label, because I'm a physics teacher, I can't have graphs without any labels. That would be outrageous. Okay, and if we go about a title, we'll call this Earth and Mars orbits. About, yeah, let's just call it like that. Okay. Right, shall we see if it works? So if we press run, there we go. Oh, that's interesting. So we just have one of these at the moment. Let's have a look. What have I done? I've just got one of them. X and Y Earth. Have I got them the same? Let's have a look. Ah, yes. I can see where my bug is. In fact, actually, can anyone see what my bug is? There we are. If you can see the bug, I'm only getting one plot at the moment. What have I not typed properly? Who's the fastest who can spot my bug? Yes, should be R Mars. Well spotted. So there we are. Right, so the radius is wrong. And we know that's true because I've only got one orbit. Oops, I've done the wrong one. There we are. Turn Earth into Mars and Mars into Earth. That's silly of me. So let's go for R Mars. Obviously, there'll be some deliberate mistakes to keep you on your toes, everybody. Right, so there we are. Let's go and save that and run. Hooray! So we've got Earth and now Mars. Now, this doesn't look like circular orbits. So let's set my axes to be equal. So there we go. So that command there will set it to be a sort of square grid. So there we go. Lovely. We might want to put a grid on as well. So these are high-level commands. You can edit the grids. You can do everything in MATLAB. And there we are. So that's quite nice. These are my orbits. Now, wouldn't it be nice to animate this? So what we can do is also plot where Earth and Mars are. So let's go for hold on. This means we can add more plots to the screen. And what we'll do, we'll go for P Earth. Right, that's going to be the kind of postal code for a plot command where we're going to have the initial Earth value. So we'll go for X Earth 1. That's the first element of my vector. If you look, I've got 5,000 possible X values. So if I just open this up here, you'll see a kind of spreadsheet of initial values. All right, so some spreadsheets can be very big, but that's basically describes all the things you've got. All right, so we'll go for X Earth 1 and we'll go for Y Earth 1. And we'll give that a blue star, shall we? All right, and there we go. And I think I'll go for marker size. I think that's the right option. Let's go for 18 points. That might be enormous, but let's find out. Okay, and what we'll do is we'll also have the same thing for Mars. I think I'll put it on a separate line so you can see. There we go. So I'll put the hold on. Let's go for here. All right, so P Earth and P Mars. So the P Earth and P Mars, this is what we call a handle. And I don't think it's particularly a MATLAB thing, but it basically gives you a number which describes the object you have created. I need to change Earth to Mars. And once we've got that sort of postal code, we can interrogate every property of that object. So I'll let's just plot it, see what happens. So here we go. So what we should have, there we are. Actually, that was a good guess for the object size. So remember, we randomize the angle. So that's where the Earth is at the moment. That's where Mars is at the moment. Now, we're going to try and animate this. So what we can do is we can set a loop here. So let's go for stop equals 0. And we're going to have a while loop while stop does not equal 0. Well, sorry, while stop equals 0. Right, so this is going to be an infinite loop. I'm going to have to manually break this. What we'll do is we'll update. Well, actually, we'll walk through the time array. So what we'll do is we'll set the object P Earth and the X and Y coordinates being the next array element. So what we'll do is we'll start off with n equals 1, and then we'll increment n plus 1, unless that n is larger than 5,000, the length of t. So what we'll do, we'll go for if n is bigger than the length of my time array. If that's true, then n is going to be 1, and I'll reset. So this means that we can keep going around our loop. All right, so I'm going to increment the element of my array, and I'm going to set the Earth's x parameters, x data. So remember, the object, my Earth object, will have all sorts of parameters. That's going to be x Earth n, and then the y data will be y Earth n, the nth value of the Earth vector. And that should be fine, and that should update the movement of my Earth. So what we have to do to make it do it, we'll have to execute the draw now function, and that should hopefully update my screen. Let's see if that works. I might need to put some pauses on this. Let's give it a go. There we go. So we've now got the Earth whizzing around. I don't know if does that come across all right? Is that coming over Zoom, or is that really laggy?
Yeah, it's good.
Fantastic. Right, well, let's go and do Mars. So what we'll do is we'll just copy and paste that and turn Earth into Mars. And I think that'll be enough for the moment, and we can add to that later. So X Mars and Y Mars. There we go. Obviously, we could, if we want, we could change the titles to have data such as the periods, etc. But you could do all sorts of things with this. There we go. So there we go. There's our orbit. Lovely. So we've got Earth going much faster, well, not much faster, but faster than the Martian orbit. So there we go. The Earth catches up with Mars, and there we go. So this is why, if you're on the Earth, the orbit of Mars is going to be quite strange. So there we go. That's our first sort of simulator, which does something exciting, and we've done that in plus some commentary, about 20 lines. Not bad, eh? There we go. So programming is cool. And I would encourage all of you to have a go. All right. So, but the key thing is make sure your commentary is put in there. Now, that's not the most tidy way I'd write it. I'd probably put the commentary before the code itself, but I'd like you to sort of see everything that's on the screen. Right, okay, I think this will be animate the orbits. And what we're doing is we're updating the X, Y coordinates. Okay, there we are. Let's go and save that. Right, any questions before we look at a few other things?
No, we're dealing with them all good.
All good, excellent. Right, okay. So obviously we're going to spend a bit more time in doing some of this sort of code live. So I probably won't go through all the slides in my presentation. So let's go and have a look. So I think I'm going to sort of skip over the next few. That's all about Kepler's law. But what we'll do is we'll find, this is challenge number 1. So challenge number 1 for the BFO challenge a few years ago was literally to plot Kepler's law. So time versus the 1.5 power of the radius, and you see an amazing correlation. The idea is I give you data like this, so you could do that in Excel or indeed in MATLAB. All right, so it's about graph plotting. Just for interest, this is data for exoplanets, so planets that are not in our solar system. Got to be careful here, of course, because the mass of the star is unlikely to be the mass of the sun. So you have an extra factor in front of it. We can still pretty much ignore the mass of any planets. The ones we've seen tend to be kind of Jupiter size or super Earth size, although that's changing rapidly now. But nonetheless, you have a factor in front of our Kepler's third law, which is the ratio of your star mass to the ratio to mass of the sun, and that can be quite a large number. So I did this for 648 exoplanets. Many more have been discovered, and you can see a very strong correlation of Kepler's third law. There are a few deviations from this. That's probably because the data is really erroneous rather than any sort of exotic physics going on. Although perhaps you might find a few with binary star systems. Now that is going to cause some problems. Right, so there we go. I think I will skip across this. This diagram here is actually plotted directly from MATLAB. So I didn't just make it. So that's where you can use this sort of ellipse plotting function. Right, let's go and find. So here's the solar system. So I think we've kind of made a simulation of that already. I do recommend, if you were to go, there's a link here, the solar system to scale. And some American guys went to the Black Rock Desert and sort of drove around in cars to give you a sense of actually how big it is compared to the planets themselves. So on that scale of kilometers, the planets are about the size of my fist or smaller. Okay, I think the Earth is about a marble. Here we go. So this is nice. We've already just done this, but on a bigger scale, you can see the animation. If you do it carefully with an ellipse, obviously you can see that Mars is actually more elliptical than the Earth. There's Venus and Mercury. So Mercury is quite elliptical as well. Right, let's go and have a little look. Here you can do this in 3D. So this is the animations for Pluto, and then going around, and there we got some more numbers. Right, so I'm going to move on. I think I was just very briefly allude to this, is that we've assumed circular motion. So I don't know if we can see, there's a lot of maths here. So let's probably not go into this in too much detail, but the idea is you can work out from Kepler's second law what the time is in terms of the angle. And in our case, it was really easy. If you like, the angle versus the time is going to be, time over period times 2 pi. That's not quite the case if you're moving around at different speeds. So if you have a really elliptical orbit, you have to do a bit of maths called an elliptical integral, which looks like this. Okay, that's why it's called it. And you can do that numerically, because unfortunately, that is not something that you can do with A-level maths. In fact, you can't do it analytically at all. So what you do is you do something called the trapezium rule, or even better, Simpson's rule. And what you do is if you have a function like this, you draw some quadratics between the data points, in fact, between every 3 data points, and you add up the areas under those. And so in the challenge, part 5 is you got to sort of code this up, and therefore you can plot some things. So for example, if you take Pluto, that's what Pluto looks like from the New Horizons probe. This is what would happen if you have a circular orbit. That's the angle versus time. If you do this properly, given it's an ellipse, there's a bit of wiggle around. All right. So if you want to do this accurately, you have to take that into account. So there we are. So that's a sort of that's a nice bit of maths of numerical integration that has a good use in working out orbits. So if you're a math fiend, then this might be a nice thing for you to do. All right. And in fact, once you've worked out of the area under a curve, you can integrate anything, okay, using a computer. Right, I'm going to sort of move on to this. So this is, I think, rather pretty. So what you do is that if you imagine this is Earth and Venus and Earth. So we've got the orbits, and what we're going to do is we're going to draw a line between where the planets are at sort of equal times. So I've said n maybe 10 times the maximum orbital period divided by 1, 2, 3, 4. So I don't know. Let's give that a go. So we're going to go back into our code, and we're going to make some of these, well, beautiful pictures. So Venus, Earth looks like this. Do I have Earth, Mars? I don't think I do. So there we go. Let's see what Earth, Mars looks like. This is Neptune, Pluto. All right. And what's really interesting is that you can actually see some of the symmetries. So Jupiter, Saturn has a kind of threefold symmetry to it. Venus, Earth has a sort of 5-part symmetry. All right, so this is to do with the kind of approximate ratios of their orbits. So let's go and back to our MATLAB code. So what we'll do is we'll step through the orbits, and we're going to draw a line. So I'm going to create as a new figure. All right, in fact, what I'll do is I'm just going to stop this one. I'm going to make sure this never proceeds. And what we'll do is, actually, we've already plotted the Earth ones. So I think that's probably, we'll edit the one we've already got. Actually, let's not have a new figure. So what we'll do is we'll step through the orbital times and draw a line between the positions of Earth and Mars. Okay, so imagine Earth and Mars have a kind of laser beam connecting them. What would that look like? Now, we may have rather too many data points, but I'm going to guess that 5,000 is all right. Let's give it a go. So what we'll do is we'll go for n equals 1 to length of our time array, 5,000 in our case. And we're going to step through, and then we're going to create a line between the positions of our planets. So what we'll do, we can already add to our plots. So that's what the hold on means. We can add to our plots. So what we'll do is we'll plot. We want the x coordinates, so we'll start off, the starting value will be x Earth, the nth value of that, and the end value in the x sense is going to be where Mars is, so x Mars, that's the nth value of that. So the square brackets are MATLAB speak for an array. So a equals 1, 2, that gives me a 1 by 2 matrix, or an array here. So MATLAB stands for Matrix Laboratory. So matrices, arrays are built into its lingo. Right, what's the y value going to be? So what we're going to be, the y value, it's going to be all of this, but y instead. So y Earth and y Mars. And let's make that a black line. Okay, so let's see if that works. It might be just a rather too many, but let's see how it goes. Right, it's thinking about it. Yeah, we've got rather too many. Right, you can start to see some of the structure, but we've got rather too many data points here. So what I'm going to do is I'm going to make that 500 rather than 5,000. Let's run that again. There we go. That's a bit better, isn't it? So in fact, might argue that's rather not enough. So let's go for 1,000. There you go. How about that? Have I actually edited this? I think probably what I'll do is just make sure we get rid of anything that's happened before. Oh, there we go. How about that? Beautiful. So there we go. We've got the Earth orbit, the blue one. We've got the Martian orbit, and then we've got a line between them, and we get this sort of slightly distorted pattern. It's quite interesting, isn't it? Okay, so it's not a nice symmetry like Venus. We've got 1, 2, 3, 4, 5, 6, and a bit. Okay. So there we are. That is a solar system spirograph. We can make it prettier by making the lines thicker. But I might do that actually. So we plotted the Earth ones. So if I go for line width and make that, I think 2 is a good number. And let's change the line width for this one. There we go. Let's just run that. So let's get rid of anything we've had before. Oops, I've made a mistake. Yeah, I've got an extra comma here. There we are. So MATLAB tells you if you've made an error. They're not usually too bad. Oh, I've still made a mistake here. It's a line 9. What have I done? It's line 2. Invalid first data argument. I think I might need to have 2 plots. There we go. So if I do this, and if I go to hold on, so I add another plot, and if I add another plot here, which is going to be Mars, I think that's okay. Yep. Hopefully that will achieve what I want. There we go. So there we are. So we've got a nice thicker line. It's a bit more visual. So the idea is we've got our orbits. So there we are. Any questions on what we've done? Hopefully you're immediately trying to give this a go. You can make a T-shirt out of this. In fact, some of the nice things, one of the best things I saw for the computational challenge a few years ago is a few people basically looked up the orbital range of exoplanets and plotted that. So they're really quite exotic. Anything in the chat that we want to talk about?
No, we have answered everything so far.
Okay, fantastic. Right, so I guess the next nice thing you want to do is say, well, does the Earth have to be? Sorry, does the Sun have to be the center of the solar system? So this goes back. This is not the Copernican model. So whose model is this, where the Earth is the center of the universe? Nina, if you can give them extra thumbs up if they spell it right. Well done. Yes, Ptolemy.
Yes, nice.
Wasn't Aristotle, I'm afraid. So we're going right back. So yes, obviously, when you learn science and actually think, oh, the Ptolemy model, that's a load of rubbish. Here we go. Here's the Ptolemaic model, right? That's this Claudius Ptolemy, 100 to 170 AD. We have these celestial spheres. It's all esoteric stuff. Well, yes, a better model is the Sun is the center. It's much simpler, but that doesn't have to be the case. We could have our model based on Earth. And in fact, if we're doing any observations from Earth, then it's pretty important that we have that model so we can post our, we can point our telescopes at the right places. Particularly if we want to send a probe to Mars or to communicate with our rovers on there. So here we go. This is some examples of the challenge plots, but we've actually got the tech to do that right now. Let me just show you a few nice ones first. So this is the inner solar system based on Earth, and you can see Mars is the one we've had. We've got the Venus one, all right, and this is the ones relative to Saturn. Some pretty ones here. So there we go. This is, of course, the Sun one looks really boring now compared to the others. I think Mercury is very pretty, particularly the Venus one as well. But anyway, and you get some mad ones like this is relative to Jupiter. I think this is quite strange. This is the outer planets relative to Jupiter, yeah, well, I quite like these. I think these are wonderfully abstract things. You makes a T-shirt, put it on a mug, something like this. Anyway, so what we'll do is we'll add that to our code, and I think that'll be the last bit of live coding. The others are more projects, which I'll show you. So what we'll do, we've got this one. So I think we'll have now a new figure. So what we'll do is we'll plot the orbits relative to Earth. So what we're going to do is we'll go back to our orbital plot, which is this one. So what we're going to do is we're going to plot orbits from perspective, orbit of Mars from perspective of Earth. Okay. Of course, the Sun's orbit from the Earth will be a circle in this sense. So what we're going to do is, we can get rid of this one here. We just want Mars, but we're going to do x Mars minus the x coordinate of the Earth. Now we can do that. We can essentially do the difference between two arrays because they have the same length and they have the same time. So every element of my Mars array, I don't know if I've got x Mars here. So x underscore Mars, let's go from 1 to 10. And I'll transpose it so you can see it nice and easily. They are the first 10 elements of my Mars x coordinates. So because these all calculate at the same time, right, I have a common, clock here for this one. We don't need to worry about relativity. So we can just literally do the difference between them. So y Mars minus y Earth. And that hopefully should give us what we want. So let's just get some X labels and Y labels. This is Mars orbit from Earth. Okay, and there we go. Right, so let's go and do that, and let's run it. So I should get two figures now, and there we go. So there's our spirograph figure, our Earth orbit and our Martian orbit. And this is our Mars orbit from Earth. And we get this sort of rather pretty looking pattern. Okay, there we go. I hope that was fun. So we just, I think I went a bit quickly. So let's just allow us to contemplate this. All right, so there we go. You can see that it's sort of not quite complete there. So it might be better to actually have a few more years. So maybe my time array could be a bit longer. So perhaps if I go for rather than 10p, if I change that to 20, that might be quite nice. So let's have a look. There we go. That looks a bit more complete. All right, it's not quite completed all the orbits yet. See at the bottom, we've got a missing one. But there we are. All right, so I hope that was fun. Let's now see a few demonstrations of some other things. So let's go and have a little skip. So here we are. So a very cool book called The Three Body Problem was released, I don't know, it was about 10 years ago. And I don't know if any of you have seen the film. Well, it's more of a TV series about it. In that case, the planet is actually orbiting around 3 stars. This is a simpler problem, which is 2 stars. So the 2 stars, the red and the blue ones, are orbiting about a common center of mass. So we know exactly what they're going to do. But the portable planet here is attracted to both of them. So if you use the right parameters, its orbits can be incredibly complex and eventually you might be thrown out of the system. So how do we go and work that out? Well, what we do is use constant acceleration motion, but in tiny time steps. Okay, this is called the Verlet method. The acceleration we can work out from the laws of gravity. So rather than show you some math, let's just go and see a demonstration of this. So I've got, there we go. Actually, I'll just show you one thing. This would be the recipe. So if you want to do this yourself, this is the slide you need. So this may look quite complicated, but basically what we're doing is we're summing up the effects, the accelerations due to gravity based on the vectors between the planet and the other stars. So I've got a vector R1, R2, R3, and we need to do the difference between those to work out the vector between our objects. Of course, those are going to change constantly as it rotates. This is why this is now a hard problem to do without a computer. So let's go and see what this looks like. So if I go onto here, I think I've got physics. It is Astrophysics. You can download all my stuff from the website. I think it's under orbit dynamic simulations. I think it's N-body gravity solver. I think it's one of these. No, it's not this one. Bear with me. I think it's binary stars and planets. Is it that one? Yeah, that's the picture. Right, so let's go and run it. Let's just get rid of that. Right, CC is my little function for clearing all the workspace. So if I run this, there we go. And I think it should start to animate. There we are. So it's quite a slow one, this one. But you can see the stars moving and my planet gradually tracing an orbit around this. Let's see if I can speed this up somewhat. Let's have a look. Time step in years. Let's have a smaller time step. And let's go for 30 orbital periods. Let's run that. There we go. That's a bit more fun, isn't it? So imagine being on this planet. Your astronomical development would be very strange. So there we are. Okay. So that's kind of fun. Now you might say, well, what happens if we have more than one planet? Could we make a galaxy simulator? So here's another little one. So if I go to interacting galaxies, I think this one is what we want. Yeah, here we go. So what I've got here is 2 galactic centers moving around each other, and the initial situation were lots of little tiny masses orbiting each star in a circular sense. But of course, those masses feel the gravitational force of the other stars. It's just like the other simulator, but I've now got loads of planets in initial circular orbits. And so if you run this a little bit, what you'll find is you end up getting structures which look kind of similar to what you see in the real world, these sort of tidal tails, right, and these sort of swirls. All right, I'll let it go one more rotation. Now this is running live, so I don't have a particularly powerful computer. What's it from? Quiet PC, a Yorkshire company, but it's a fairly standard one. This is running live. Okay, so you don't need a supercomputer for this. There we go. So I've got a few other illustrations to show you. Let's have a little look. So there we are. So my interacting galaxies. You can obviously this first one has 11 a mass ratio of 11 to 3, which sort of like devours the other galaxy. And this is kind of what it looks like. This is a 5 to 3 ratio. And you can see its progression with time. So there we go. That's the Messier 83 galaxy. And you can see these sort of spiral forms with these sort of tidal tails. Though obviously, you've got a vast, billions and billions of stars. All right. That's a sort of one with some random masses, which interacting via gravity. Not sure how physically realistic this is. And of course, you do get ones with multiple orbits, although they tend to be sort of regarded as binary systems, but lots of them. So in the center of our galaxy, Sagittarius A star, where we think there is a supermassive black hole. So you can look at the motions of all these stars, but they are all ellipses, and from that you can kind of guess what the mass of the thing in the middle is, which is about 4.2 million solar masses. There we go. Right, so this might be the last sort of thing we'll do, is the tidal forces. So if we're on the Earth, all right, and the moon goes around us, we've got this layer of water. And the geometry here is basically sort of looking at how the center of the moon looks is a sort of projected from a point on the surface. And what you'll find is, of course, because there is an extension to the Earth, the strength and the direction of gravity will be different around the Earth, all right? And although that's a small effect compared to, the gravity, causing the moon to orbit around the Earth and the Earth around the sun, it's nonetheless powerful enough to drive currents in the water sloshing around our planet. So with that in mind, I have a simulation of this, which could be the last one I think we'll do today. So if I go to Tides and Tide Sim, so what we're going to do, these are the input. These are the sort of data for the Earth and the Moon, but we're going to do something a bit more extreme. So we'll have the Moon being half the mass of the Earth, and the distance, the orbital radius, will be 3 times that of the Earth. Right? Because the Moon one is quite boring, really, compared to this. And then what I'm going to do is I'm going to have lots of little masslets that are orbiting in a circular sense around the Earth. That's going to represent the tides that rotate with the Earth. So if we run this, hopefully this will work. There you go. So this is the planets, and this is my enormously unfeasibly thick water layer, and this is my moon. So what you see is the water layer is being distorted quite heavily by my moon as it goes around. So I end up with these rather large tidal bulges that rotate around the planet. Now, let's make the mass a bit bigger. Let's see what happens. So if I quit that and make, say, well, actually, maybe let's take the moon be a bit closer. So rather than Earth over 3, let's go for 2.5. Let's see what happens there. Whoa, look at this. So there we go. So my tidal bulge is really impressive now. And although this may sound like a really mad thing to do, it's thought that, it's a known fact that the moon is moving away from us about the rate that our fingernails grow. We know this because we have a laser sort of reflector on the moon from the Apollo missions, and we fire a laser towards it. Oh, we're starting to eat the atmosphere now, or eat the water. And so we can work out how far the moon is to exquisite precision. We're talking millimeters, I think. Be sort of actually maybe even close to the wavelength of light. So that would be much, much less than that. So if you wind back time billions of years, that implies the moon was quite close to the Earth. such that the tides would have been enormous. And it's thought that this sort of sloshing of water in the early Earth might, just might, have helped the development of complex life, which otherwise would be, quite a rare occurrence for, parts of cells to get in other parts of cells, such that we have a mitochondria and all the things which allow biology to work. So there we go. I'm not sure I'd want to be on this planet. I think the tides are a bit too scary for me. But there we are. Produces a kind of pretty looking pattern. So I think we will stop there unless anyone's got any burning questions.
Nope, answered everything.
Fantastic. Well, thanks for coming. I think next week is special relativity. So all this Newtonian clockwork stuff, I'm afraid that's not quite true. So if you want to know about special relativity and about how hamsters and ducks are related to that, you know where to go next week. Thank you very much indeed. We'll if you could sort of disappear and get yourself a nice warm drink. Thank you very much, and see you next time. If we could stop the recording, that'd be awesome.